Ayaz, and today we're going to discuss about a hybrid deep model for brain tumor classification. Classification of brain tumor types with MRI imaging using computer-aided diagnostics tools and methods have some major challenges. CAD systems work with intensive pre-processing produce better results as compared to those CAD systems which use no pre-processing or minimal pre-processing. The main idea of this work is to construct a two neural network method that produce architecture that works in a fusion of hybrid deep network architecture. Evaluation of deep model through statistical analysis made this work more strong in terms of achieving higher accuracies. Brain tumor classification is considered as the second most fatal emergency after Alzheimer's. They are found in every age groups, from child till the elderly peoples. This study investigates between three major types of brain tumors: glioma, pituitary tumors, and meningioma tumors. Although current CAD systems use machine learning approaches to use and classify these type of tumors, but they consume extra pre-processing and can have greater computational cost in terms of time and accuracy. Manual analysis is still over there. We use neuroradiologists, and oftenly they are prone to error due to the issue of consistent working. Radiologists have a hobby or have a habit to work in the intensive care and intensive hours. Sometimes they are not manually present enough to actually classify between these tumors due to bad imaging or some sort of disturbing or some sort of events they are facing at that time. The background of the work is very extensive. Multiple work has been produced to perform better classification of brain tumors. And those tumors or those type of classification identification are done with normalization, regional contrast-based technique, segmentation. The figure explains the three type of tumors and their segmentation of particular area through region of interest selection, and then finally goes to morphological operations. This work eliminated the use of those techniques by achieving higher accuracy without that augmentation, segmentation, and pre-processing techniques. Artificial intelligence is a major component in MRIs and CAD systems because they produce good results and achieve higher accuracies in the recent world. Machine learning and deep learning approaches as state of art has been used in multiple techniques and multiple tools to produce good results. For conventional methods, feature extraction has been used for machine learning purposes, and today's state-of-the-art methods are deep learning models. When we talk about artificial intelligence and conventional method, traditional methods of machine learning has some serious flaws. These are not flaws, even actually. These are some sort of computational limitations we have right now, and that are overdone by deep learning models, such as data augmentation, which is done in both deep models and machine learning techniques, image pre-processing and image segmentations, region of interest selection, and then goes to feature selection method to achieve better classification results. The limitation is that increase the computational cost and time complexity, which make the CAD system an expensive method. Deep learning is widely used in classification problems for medical imaging. They extract good quality feature in terms of shapes, edges, orientation, texture, statistical features. The following equation state the convolution operation, kernel filtration, and the feature map are for each layers. It overcomes the limitation of traditional machine learning methods. This study consists of two different highly used networks that are AlexNet and SqueezeNet architecture. For SqueezeNet architecture, we used one fire block instead of nine fire blocks that has been originally produced in 2016. Merger of these two features together then goes to non-linear hidden dense layers made a good quality of network that produced remarkably with 3Ds type of tumors. For training and testing, we divide the dataset into 80-20 ratio. The acquired image size was 5112 cross 5112 with one channel of MRI, which was then reduced to 256 cross 256. As many people have suggested this particular type of dimension, therefore we stick toward this particular dimension, and it reduced the computational purpose a bit good to achieve a very good accuracy. To reduce overfitting issue, we use the early stopping method uh, for each validation loss to go decreasingly each and every five epochs. If the loss was not going down after five epochs, the whole validation of cross validation has been stopped at that particular time. Finally, we use 10K full cross validation for training data. The experimental results shows that different type of optimizers produce different type of results with this model. RMS produces very good result with 94% accuracy. We train on 415 images and tested on 613 images. Seven optimizers with their known learning rate produce a very good results. As we know, for the optimization of a model, learning rate is a very sensitive issue, and it produces good and bad results and make sure that the overfitting and underfitting of a model converge or diverge at that particular point. The particular image shows the learning curves of our model with very good results in every time fold class training, fold 1 to fold 10 accuracies and loss. Uh, this convolution operation for statistical evaluation shows that the glioma has 28 misclassification of meningioma, as the MRI was very similar to one another. We yet need to work on the particular identification methods so that we can make sure that the classification of these two tumor types have been done remarkably with no or very minimal misclassification. We did proceed and recall NFN score for the statistical evaluation of our method that can be seen in table 3. In conclusion, this research investigates a hybrid deep model for classification of 3 tumor types. The overall accuracy achieved by our model was 94%, and with 10 epochs and minimal pre-processing to require the accurate CAD system. Why this method works with the 10 convolution is that the feature extract from different models are very good and healthy make of a feature fully connected network. The proposed idea opens the door toward the new possibility of merging deep models and making a hybrid deep model approach for tumor classification. Current and future direction of our works are to enrich the data type and enrich the data tumors that we have. We are not sticking toward just brain, and similarly in different type of tumor types in our brain, we're going towards sinusal tumors, lung cancers, spinal tumors, lymph nodes, as well as within glioblastoma for brain tumor classification between HGGs and LGGs. In future, we will try to work with the fusion to reduce the data redundancy caused by the merging of the two networks using autoencoders, and also which will also help us to identify the misclassification of meningioma class in glioma classification. These are some of the reference I have used to make the presentation. Thank you. I will look after your questions.